All right, this is section 7.1, integration by parts. So in this section, we're going to learn a new way to evaluate integrals that we couldn't do earlier. So far we just have the power rule and the substitution rule as the main focus, right, when it comes to it. And a little bit of trig when it comes to it, but mostly just those two as our main arsenals of integration. So this time we're going to learn a new way of integration called integration by parts, where essentially is, well, what if you have like two different functions put together, like sine and cosine put together, how would we take the integral of both, that function altogether, which we couldn't do earlier when it comes to it. So how will we do that? Okay. So this way, integration by parts is kind of broken down to like this, where we're going to integrate f and g prime. Okay? And this is equal to f times g minus integral of f prime g. Now, this is kind of confusing, right? I was never taught this way, and again, this is the proper way to do this. But the alternative way, which way it makes it easier, have all these f and g's and parentheses everywhere, is what we're looking at let u equal f of x, and we let v equal g of x or g prime of x. No, that's right. Let v equal g of x. Then what this integration by parts looks like is the integral of u dv is equal to uv minus integral of v du. And it's much easier to understand that portion, having all that, integration stuff and all that f and g's when it comes to it. Okay. So essentially what this is saying is, let u equal f of x, and then dv equal g prime of x, and we're just going to go backwards and find v. We're just going to integrate it, and then we'll plug it into the equation itself. But again, if you remember vu minus integral of v du, that's pretty much what this integration by parts is all about. Okay, so let's show an example so you can see what it means by all these v's and u's when it comes to it. All right, so let's look what we have here. We have x times secant of x tangent of x. So we have a couple things happening in here, right? So what you want to do is you want to make u equal to something that's easy to take the derivative of. Okay. So we're going to let u equal x. Okay. And therefore, by default, dv is going to be everything else. So in other words, secant x tangent x dx. So we literally just separate them. Okay. And now we're just going to go down. So we're going to take the derivative is just going to be 1. And now here we're going to take the integral of that. Now remember, just if you're not sure what the integral, you can always go back to the first page. I give you that set of integration. So the integral of secant tangent is just secant, which makes it simpler to deal with. Okay. All right, so now that we have this, so now we're going to write this down what it is. So following this template, it's going to be u, so x, times v, which is secant, minus the integral of v, which is secant again, times du, which is just 1 dx. And now notice it's actually not that bad anymore. Okay? So we don't have to integrate this anymore. We just have to integrate that and just go from the motions there. So this ends up being, again, x secant x minus the integral of secant, because it's 1, right? So the integral of secant is going to be the natural log of secant x plus tangent x plus c, and there is our integral. So that's how it's what's called integration by parts, where when you go down you take the derivative, and you go up you take the integral. So it's just the opposite order when it comes to it. And that's why I say sometimes you want to find u where it's easy to take the derivative, or vice versa, where it's easy to take the integral of going backwards, because sometimes you get stuck and you may actually have to swap places when it comes to it. Okay. So let's try the next one. All right, so find the integral of 4 natural log of x dx. So this is a trick one when it comes to, and it's very popular as we go throughout the semester as well, taking the integral of natural log, because technically we don't have a property for it. So we have a property for integral of 1 over x, right? That gives the natural log, but how do we go backwards from natural log? So that's what we're going to be learning here. And it's only being able to do this by using the integration by parts. Okay. So like I said, we always want u to equal something we can take the derivative very easily. And that is just natural log of x, right? Because we know that the derivative of natural log of x is just 1 over x. So it's just going to be 4 over 1 over x, right? Times it. So therefore, And this is the very interesting part. We're looking at dv equal the dx portion, or in this case just 1 dx. So therefore, if we take the integral of that, that's just going to be x, right? Integral of a constant, just a constant with the x value, so same thing applies here. That's why it says kind of a trick question. So now, therefore, using our integration by parts, it's going to be a u times v, so u times v, so 4x natural log of x, minus the integral of v du. So 4 over x times x, and notice that actually cancels out. So those actually go away. So it's just the integral of 4, which is again just a constant, so it'll just be 4x. So this is going to be equal to 4x natural log x minus 4x plus c. And there we go. All right, now let's try a hard one. So that's the reason why I have a little scary face here. This is a pretty tough one because it combines a couple of different type of things into one. Okay. All right, so same thing. We're going to find the integral of now x times cosine, and within it 2x, right? Cosine of 2x in there. Okay. All right, so we're going to let u equal x, and then dv equals cosine of 2x. Okay. So this derivative is just going to be 1. And now this integral, what's the integral of cosine of 2x? Probably something you don't know off the top of your head, right? So on the side note over here, we have to make a little note. We got to find the integral of cosine of 2x. So this is actually using the substitution rule. So let's say u equal 2x. So therefore du equals 2. So we don't have anything, so we just divide it by half. So this is the integral of 1/2 cosine of u du. So integral of cosine is equal to sine. So this is now sine, or 1/2 sine of u, and we just plug that in. So this is actually 1/2 sine of 2x. So just got to be careful about that, right? So as always, a straightforward because we have numbers inside of here now. Okay. Right now we have this done. Now we just plug it in and see what we get. So plug it into our formula. It's going to be, again, uv. So this times that. So it's going to be x over 2 sine of 2x minus the integral of v du. So this times 1 is just itself. So I'll just bring the 1/2 on the outside. And gives us that. Okay. And now notice we have the same situation again. Okay. So again, doing a little note, because we now have to take an integral of this. So we'll have u equal, again, 2x. Therefore, du is equal to 2 dx divided by half. So it's 1/2 du is equal to dx, which is what there it is. So we're now plugging that in. This is negative 1 over 4, the integral of sine of u du. All right, and then the integral of sine gives you I think a negative cosine. So okay. So this is going to be negative, or negative becomes positive, 1/4 cosine of u du. So finally, our final answer of this portion is going to be x over 2 sine of 2x plus 1/4 cosine of 2x plus c. And there we go. This is what I consider a pretty difficult question, because notice that we had to do a substitution rule actually twice. Once for the initial one, and then again for the actual integration in our portion. Okay. So fun little one there. Okay, So this also applies when it comes to the bounds, right? So, whatever we could do for just regular integration, we could do with bounds themselves. So the rule for when it comes to bounded integration by parts is the same process.